Hello students, welcome to this lecture on interconnects. So in this particular part of the lecture, we will start with the repeaters, importance of the repeaters in a long interconnect wire, and then proceed further to see how do we design the repeaters, and how many number of repeaters we require so as to optimize, what is the optimized number of repeaters that is required to minimize the overall delay. And later on, we will see what happens to the characteristic energy properties for a long wire with the repeaters and without the repeaters. So repeaters in general are nothing but in a digital circuit, it is nothing but an inverter or a pair of inverters, so that your overall signal strength, while it reaches to the other end of the wire, it is still the same signal strength as that of where the signal has started or propagated from. So you can consider, if I have one inverter and then another inverter, and it is kind of connected by a very long wire, then the output of the first inverter, when it is, there is a signal at the output of the first inverter, and if it has to propagate along this long interconnect or a long wire, till the time it reaches to the another part of the inverter, the signal strength might actually get attenuated. And so we add some inverters so that the signal strength improves, and we have relatively a stronger signal while it is reaching at the other end of the wire. So that is just a brief introduction. So let's start looking into more details. So this is what I had said earlier. We have a driver circuit, which is, in this particular case, it is an inverter, and then we have a receiver circuit. Again, it is, I've drawn an inverter here, and then let's say that we have a long wire here. So if the signal starts here, the output of the driver inverter circuit, and by the time it reaches here by a long wire, the signal might actually get attenuated, right? So in that sense, if I draw that signal, you have 0 to 1 here. So at the output of the driver circuit, I have 0 to 1. So at the input of this receiver signal, if I have a really long wire, then I think it may not actually, the 1 voltage may not be 1 voltage. So this is actually the 1 value, but here I'll get an attenuated signal. It could be 0.6 volts, or it could be 0.7 volts, and so on. So there will be an attenuation based on the length of the wire. So there will be a signal loss. So in that sense, we need to add some kind of a repeater circuit so that you get the expected signal level. Now here in this particular circuit, in this particular schematic, what I've shown is a long wire connecting the two inverters. One is the driver and another one is the receiver. And I've stated that this is the length of the wire. So L is the length of the wire. And that the wire or an interconnect can always be represented in the form of an RC circuit. So a distributed R and then a distributed capacitance is here, and then this is of the wire. So I'm going to write it as RW and then CW. Now this RW and then CW is nothing but, so let me rewrite this as R wire and then C wire. So this is the overall resistance of the long length of the wire. And C wire is nothing but the overall capacitance for the long length of the wire. So if I consider the R wire, by definition, it is nothing but the resistivity of the wire. In this case, it will be copper. And then the length of the wire divided by the width multiplied by the thickness of the wire. So here it is actually directly proportional to the length of the wire. C wire, if I go by definition, it is nothing but epsilon naught K oxide. We'll assume that the dielectric is nothing but silicon dioxide, and we have the area, which is nothing but L into the width of the wire, and of course divided by the spacing. So this H is representing the spacing between the two wires. So if I consider this to be a ground plane, so then in that sense I will have whatever is the spacing will give me spacing between this particular long wire and then this particular ground plane. Whatever is the spacing here will give me the capacitance. So here also the capacitance parameter is also defined by the length of the wire. So if I am going to evaluate the overall delay, the overall RC delay of the wire, RW is directly proportional to the L, CW is directly proportional to the L. So my RC delay of the wire will be directly proportional to the square of the length of the wire. So what it really means, it means that as I increase my length of the wire, the overall delay from this particular point A to this particular point B, right? The overall delay for the wire, for the signal to propagate from the A part of the wire to the B part of the wire, is directly proportional to the length of the wire. So if I increase my length of the wire, the overall delay is likely to, is naturally to increase by the square of the length of the wire. So if the length of the wire is 1 mm, I will have it directly proportional to the 1 mm square. If tomorrow the length of the wire is actually 10 mm, so it is going to be 100 times more than that what we have, what we had acquired for the length of 1 mm. So that is something we have to look into it, because we don't want the interconnect propagation delay, or the delay due to the interconnect, or the delay due to the wiring, to be very, very large than that of the computational delay. So the driver and receiver, it could be, substituted, some other combinational circuits than that of whatever I have shown here. Instead of the inverter, it could be any kind of a combinational circuit. And if that is the case, the computational delay, whatever we'll achieve, and that should not be, that should not be dominated by this overall length of the wire. So we need to do something about it. So one of the statements I have written in the slide here is, if a wire is split into n segments by inserting an inverter or a buffer called as repeater to actively drive the wire, the RC delay of the wire is proportional to the L by N, the whole square multiplied by N. So let's have a look at it. So there are two problems here. One problem is the attenuation problem. So this is one problem if I have a long interconnect or a long wire. The second problem is the RC delay of the wire is directly proportional to the square of the length of the wire. So let's once again look into this long wire. So let's say that I have a long wire, and then this is A, and then this is B. So at A I will have a driver circuit, and at B I will have a receiver circuit. So let's say I'm going to add a repeater so that its attenuation gets improved. So while it reaches to the point B, it will have the same signal strength as that of the point A. So I'm going to add repeater, and I'm going to add n such n minus 1 repeaters, so that I will actually segment the wire into n segments. So I'm going to add a repeater here. I'm going to add a repeater here, repeater here, repeater here, here and here. So I'm going to say that this is dot dot dot. So I will have this. So I will make the wire into, now divide the wire into the segments. So this is segment number 1. This is segment number 2. This is segment number 4, 5, dot dot dot, and then this is my nth segment. So I have divided the long wire into n segments. And let's say if it is equally divided, then I will have the length as L by N, the length as L by N, and the length as L by N, length as L by N, and I will have dot dot dot, and then length by N by N. And let's say that, this overall length of the wire is L. And if I separate the long length of the wire into n segments equally, then I will get each segment's length as L by N. Let's say that the long wire is also characterized by RW and then CW per unit length of the wire. So what it means is RW is the resistance per unit length of the wire. The units will be ohms per whatever, millimeter or meter. CW will be again femtofarads or picofarads. So I'm just going to write at femtofarads per length of the wire. So it is kind of characterized, the interconnect of the wire is kind of characterized for unit length of the wire, per unit length of the wire. So if I have L by N here, the overall resistance of this particular segment, segment number 1, will be RW, L by N. The capacitance for this segment will be CW, L by N. Similarly, for this segment number 2, I will have RW, L by N, CW, L by N. For the third segment, I will have RW, L by N, CW L by N, and so on till it reaches the nth segment where we will have RW L by N and then CW L by N. Right, so the first thing is the repeaters have been added here at each of the n-1 segments, so that my overall signal strength, while it is the signal starts from A and while it reaches to the B, we will have a good signal strength, not an attenuated anymore. Remember that this particular repeater, it's nothing but in the form of an inverter. So if I consider the inverter here, at each of the repeater points, n-1 points, I will have a VDD rail or I will have a ground rail. So what it implies is at the output of this, it will be either be driven by a strong VDD signal or a strong ground signal. Right, so based on the input signal, we will get the output to be a stronger logic 1 or a stronger logic 0, and in that sense, I will have a strong signal here while it reaches to the point B. Right, so if I have even number of inverters here as a repeater, then in that case, my logic, whatever is there at the point A, will be same as that, that will be reached at point B. And if I have odd number of inverters, of course, the logic will be complementary at point B with respect to the A. There is one another way of having the repeater is each of these points, instead of an inverter, it could be a pair of inverters. So an inverter very, very close to another inverter. So we'll have a pair of inverters, so that in that case, at each of these repeater points, I will have a pair of inverters. And at point B, I will get non-complementary logic. Right, so there are different styles of designing the repeater, but the overall aspect of the repeater is making sure that we will have a non-attenuated signal at point B, at the other end of the wire. Okay, so coming back to this particular the segment, right? So if I have created n segments, so the overall, or rather the delay of one particular segment, so I'm going to write it as a delay of one particular segment as an RC delay will nothing but it will be nothing but RWCW L by N the whole square. And the overall delay for the wire, which is of n segments, will be nothing but the summation of RWCW L by N the whole square from one segment to n segments. So it will be nothing but n multiplied by RWCW L by N the whole square. So which will be nothing but RWCW L by, or rather L square and divided by N. Now this is very important. It's still, even if I segment into n segments and add the repeaters here, I will still get, if I increase the length of the wire, the RC delay of the wire is still proportional to the square of the length of the wire. Right, so it is not going to get eliminated. But if somehow I make this L by N, right, as a constant, so what it means is, so if I make this as a constant, so if I have, based on the length of the wire, if I can proportionally add the number of repeaters, if I proportionally divide the length of the wire into n segments, if the L is, if the L is 100 millimeter, then, with respect to 1 millimeter, whatever the number of segments I have created, so if it remains proportionally, right, linearly proportional, so the number of segments I'll create for 100 mm will remain linearly proportional with respect to the number of segments I've created for a long length of wire of 1 mm. So in that case, if L by N is a constant, or it is directly proportional to the number of segments, then I can actually eliminate, the RC delay will now be directly proportional to the length of the wire. Right, so coming to this particular slide, so what I mean is RC delay, as we have seen, is directly proportional to the L square by N. But if somehow the number of segments is made proportional to the length of the wire, the overall delay increases linearly with L, right, which is a good factor compared to when we had an L square by N, right, or without even making the segments, it was directly proportional to the L square. So in that sense, if I somehow make L directly proportional to the N, that means L by N is some kind of a constant, right? So then my RC delay of the overall wire will be linearly proportional to the L of the wire, the length of the wire, right? So what it really means is, if suppose the number of segments I've created is, let's say, phi for the length of 10 mm, right? And tomorrow, if I want to design in some other portion of the chip a 100 mm wire, the number of segments I'll have to create for this particular length of the wire will now be 50. So it increases proportionately as the length increases, and in that case my RC delay of the wire will now be directly proportional to the length of the wire. It will have a linear relationship with the length dimensions of the wire, and not the square of the length of the wire, right? Hope this is clear. So if we understand that, then I think we will now try to arrive at that particular relationship between the length of the wire and then the number of segments. So in the last slide, we had seen a segment of the wire, and then I had made n segments. So here, what we have done is, at each of the segments, not only the segments are created, but also a repeater is added, right? So here, so we have created, this is point A, and then let's say this is point B. And at each of these segments, wherever the segments are created, there is a repeater being added. So this will be my segment 1. So let's say that, this is my segment 1, and this is the segment 2, then the segment 3, segment 4, segment 5, and minus 1, this is the segment N. So I've created n segments, and not only created the n segments, but also have added the repeaters here. Repeater 1, repeater 2, repeater 3, repeater n minus 1. Right now, if I add the repeaters, then I will have each of the segments of length L by N. So that's what I've written here: L by N, L by N, and L by N. And if I look into this particular aspect of the, or rather the second segment of the wire, where we have the L by N length of the wire, and on each side I have a repeater number 1, and then the other side I have a repeater number 2. And in this particular case, I have drawn an inverter. Right? I've just taken a simple example of the digital circuit, and instead of a repeater, or rather, in the form of a repeater, I've added the inverters. So I have an inverter 1 and inverter 2, and then in between that I have the one segment of the wire. The length of the segment of the wire is L by N. And each wire can be represented in the form of a pi model. RW L by N will be the resistance of that particular segment. The overall capacitance is CW L by N. But in the pi model, we know that half of that particular capacitance will go in one side of the resistance, and on the other side of the resistance, other half of the capacitance will go. So that's why the capacitance of CW L by 2N and CW L by 2N is there on the two of the sides of the resistance. The repeaters, which is nothing but an inverter here, and its switching resistance and then the parasitic capacitance is drawn here. So the parasitic capacitance is, I have stated it as C. Based on the width of the inverter, we will have CW, and this is a normalized parasitic factor written as rho inverter. Up till now, we had seen the parasitic factor of an inverter to be nothing but 1. Right, and then in the future slides, in the immediate future slides, we will see whether it can be less than that of 1. If it is less than that of 1, then it will be good, because my overall capacitance will be less, which will help in reducing the overall delay. This is the switching resistance of the repeater number 1, or the inverter in this particular case. CW turns out to be the input capacitance or the gate capacitance for the repeater number 2. Right? And let's say that, this is the repeater number 2, what I have drawn here. If it has a width of W, then I will have C into W. And if the repeater number 1, which is nothing but, this is the repeater number 1, and which is nothing but an inverter number 1. And if it is of size W, then I will have CW rho inverse. Right? Remember that RW and then CW are the resistance and the capacitance of the wire per unit length of the wire. And then C and R are nothing but the capacitance of the unit inverter and then the switching resistance of the unit inverter, right? So up till now, what we had seen for a unit inverter is, so let me draw the unit inverter. And this is my unit inverter with the VDD rail and then the ground rail. And let me take up the unit inverter as 2:1. So in my 2:1, I always used to have a 3C capacitance because 2C capacitance coming from the PMOS side and 1C capacitance coming from the NMOS side. Now in this particular case, this C is actually nothing but 3C capacitance, where C in this particular case was nothing but the unit, NMOS transistor. So that is what we used to take, right? That particular C value is nothing but a unit NMOS transistor. Whereas here, this particular C is nothing but this 3C of the unit inverter, right? So just for your own understanding, this C is actually nothing but 3 into C if this C is nothing but unit NMOS transistor. But I consider this C as nothing but the capacitance of a unit inverter, right? So that's all the difference. If it is scaled by W times, then I will have 3C into W, I will have C into W. Right, and then the parasitic factor, if it is 1, it will be C into W. If it is something else, it will be CW into rho inverter or the parasitic inverter. All right, even the gate capacitance here, so the same inverter I can draw here, 2:1, and the PMOS and the NMOS, and then the gate capacitance should have been 3C, assuming the C is nothing but the gate capacitance of a unit NMOS transistor. But this C is nothing but of the unit inverter. So this C includes 3 times the unit NMOS transistor's capacitance. So similarly here, this C includes 3 times the unit NMOS capacitances, right? But this C I have just written it down as capacitance of the unit inverter. All right. So note that particular difference with respect to our previous lectures. The switching resistance of the unit inverter will be nothing but so let me rewrite this. So the switching resistance will be nothing but R, and then the switching resistance will be nothing but R. Right, so that's what I have stated here. And then if it is scaled by W times, I will have R by W. So that's what I have written, switching resistance of the unit inverter. So hope the RW, CW, R and C values are clear at this particular point of time. Remember that we have a driver with the scale of W, or rather not the driver, the repeater with a scale of W and repeaters with a scale of Ws, repeater n-1 with a scale of W, and RW and CW is nothing but the resistance and then the capacitance per unit length of the wire. So hope this is clear. So now let's have a look at the normalized parasitic factor, the normalized parasitic delay in our linear delay model. So I'm taking an example here of 24 lambda and 12 lambda. Let's say that it is nothing but the 6:3 inverter. So 6 inverter, represents 6 into 100 nanometers. So that will be 600 nanometers, and then 3 represents 3 into 100 nanometers. Right, each of the 100 nanometers is nothing but 4 lambda. So normally the unit NMOS transistor has a minimum of 4 lambda. So a scale of 1 represents 4 lambda, which is where lambda is 25 nanometers. So if I consider that, that will be 12 lambda here, and this will be 6 into 4 lambda, 24 lambda, and that's what I have written here, 24 lambda and then 12 lambda. Right. So if I have this 6:3, then my output capacitance is actually, the parasitic capacitance is 9C. The benchmark inverter for this particular case will be nothing but 6:3, because I need the same output current, whether it is discharging current or the charging current, it will have a capacitance of 9C. So the benchmark inverter will be 6:3. So my normalized parasitic factor will be 9C divided by whatever the benchmark inverter's output node capacitance is, and that will be 1. All right. Now, if I look into the folded technology, it's kind of a, we have this as a conventional design, and then this is a folded technology. And so what we have is basically 2 inverters, right? 2 inverters. where the inputs are connected and where the outputs are also connected. So I have an input here and I have an output here. The size of the this particular inverter will be nothing but, if it is 6:3 here, I'll make this size as 3:1.5 and 3:1.5. Right, put together this 3 plus 3 will be 6, and then 1.5 and 1.5 on the NMOS side will be nothing but 3. But let's say that if I make this 3 and 1.5, so that means 3 and 1.5 on the PMOS and NMOS width, and then 3 and 1.5 on the another inverters PMOS and NMOS width. So this is PMOS, and then this is also PMOS, and then NMOS and NMOS has 1.5. My input capacitance will still be 9C. But now the output capacitance, I've written it as 4.5C, because the diffusions here, which are in parallel, are kind of merged or shared now. And then the diffusions here on the NMOS side and then on the NMOS side are also shared, and they are merged. So my overall capacitance here, because it's a merged or the shared the diffusion, I'll get 3C from this particular diffusions. And then I will get 1.5C from this particular diffusions. So I will have the shared diffusion capacitance as 4.5C instead of a 9C. The gate capacitance does not change, it will still be 9C. Right, moving forward. So this is what I have drawn, the stick diagram here, just to ensure that, just to give you a more detailed representation of the diffusions. So this is the P diffusion line, this is the N diffusion line. I have a VDD rail, I have a ground rail. So if I consider this particular portion of the inverter, the left side of the inverter, I've drawn it on the left side in the stick diagram also. So I have a polysilicon gate, the red line, which divides the P diffusion into two diffusion pockets. On one diffusion goes to the VDD, because this is what goes to the VDD. The other diffusion is my output line. The other diffusion is the output line Y. Right, on the N diffusion side, I'll have the input. This is the polysilicon gate input. On one side it goes to the output line, so this is my output line. On the other side it goes to the ground. So this particular diffusion goes to the ground. And if I consider this the right side inverter 3:1.5, so I will draw the similar mirror image of this particular inverter in the stick diagram. I'll just draw it the mirror image. This on one diffusion it will go to the VDD, N diffusion line, one diffusion goes to the ground. On the other side it is nothing but the Y output, on the other side it is nothing but the Y output. So what it really means is, this particular part of the diffusion is actually shared diffusion. It's a shared contact, because there is a output line which gets connected from P diffusion line to the N diffusion line, and even in the N diffusion line, this is actually shared. Right, so if this is shared, the diffusion widths will be 1.5 and 3C only, and not 6C and 3C. So my overall capacitance in this case for the shared diffusion capacitance will not be 9C, will be 4.5C. The gate capacitance will still be 9C. Right, because the gate capacitance is nothing but the accumulation of all the capacitance at the gate side, which will be 3, which will be 1.5, which will be 3 here, and 1.5 turns out to be 9C. All right. So the normalized inverter in this case will be nothing but the output capacitance 4.5C, and then divided by the benchmark inverter. In terms of the conventional design, the benchmark inverter will still be now if it is if I consider the charging current and then the discharging current that is going to that is coming from the VDD rail and then going to the ground rail, it will still be, the benchmark inverter will still be 6:3, because at the VDD the charging point, and at the ground rail the discharging point, the current that goes to the ground rail for while it is coming down will still be 3i, and while it is charging from the VDD rail, it needs to still be 3i, right? As compared to here, the current is actually 3i here, and while it is discharging to the ground, the current is actually 3i. So the output current while it is discharging or while it is charging for 4.5C, it will still be 3i, and for defining my benchmark inverter, it has to be a conventional benchmark inverter should be 6:3. So my normalized inverter in this particular case will be 4.5C divided by 9C. So it will be nothing but 1 by 2. Right? Hope this is clear. Now this forms a very important aspect in our this particular row inverter will be included in our repeaters, especially in the delay part, to estimate the delay as well as to estimate the energy. We will see this particular row inverter, which is nothing but it could be 0.5 or it could be 1, depending on what kind of the design technology we'll be using.